In this lesson, we're going to look at what we mean by chemical equilibrium, and we're going to look at the relative amounts of reactants and products based on an equilibrium constant K, which we will also discuss. We see that our reaction rates are equal and that the amount of products and reactants is not changing. So the reaction will still continue to run. We will still have A going to B and B going to A, but they will be happening at the same rate. And we will see the amount of B does not change and the amount of A does not change, that those values are constant. So if we looked at a snapshot at any one particular moment, a specific molecule may not be present as A or B, but their amounts of those substances are changing, but those amounts are not necessarily equal and are usually not equal to one another. So the equal comes from equal rates. Now we mentioned earlier the equilibrium constant K, and it tells us about the ratio between reactants and products. Now this constant is constant to a point, but it's for a specific reaction under specific conditions. So if I have a different reaction, or different conditions, I'm going to have a different value of K. But for that particular reaction or any particular reaction under a set of conditions, the value of K will be constant. So for example, if I was looking at the reaction represented here, A plus B going to C, notice I have my equilibrium arrows, which indicates the reaction is going in both directions. We could calculate the value of K, and this is the expression, which we're not going to look at quantitatively, but we could set up an expression to calculate K. No matter how much of each of my substances I started with, it would always go to equilibrium. That's kind of like a reaction's happy spot. It's going to progress no matter where it starts until it gets to equilibrium. We can even put in just C at the beginning of a reaction, and it will decompose into A and B, and it will continue to do that at a faster going in the reverse than the forward direction until it gets to equilibrium. And once it's at equilibrium, the rate of the forward reaction and the rate of the reverse reaction will be equal. The concentration of A will be constant, the concentration of B will be constant, and the concentration of C will be constant, but they will not necessarily be all equal to one another. So we can actually figure out and quantify the value of K. We're just going to look at this kind of qualitatively, and what we see is that the value of K equals the concentration of products over the concentration of reactants. Now, when we look at the expression for K, what we see is that there are no exponents on any of these terms, and that's because there are no coefficients in front of these substances. If we look down here at the bottom reaction where we have coefficients of 3 and 2, because remember, no coefficient means a coefficient of 1, so we have 3 and 2, that difference is reflected in our K expression. So we'd have F to the second power because of the coefficient there. Again, what we're worried about is the general setup of products over reactants. And we want the concentrations of those species and that's going to give us something about the value of K. Now let's look at the relative values of K to determine whether reactants or products are favored. And when we say the reactants or products are favored, what we're saying is, are we going to have a lot of products or a lot of reactants? And so that if we have a lot of products, that means we have a small amount of reactants. If we have a lot of reactant, that means we have a relatively small amount of product. And even though the reaction runs in both directions, remember that we talk about everything on the left side of the arrow based on the way it's written as our reactants, and anything on the right side as our products. So let's first look at when the value of K is greater than 1. So when we look at a value of K greater than 1, what that tells us is that the numerator is larger than the denominator. So the numerator is on top, it's larger than the denominator on the bottom, because that's the only way we could get a value greater than 1. Think about it in very simple terms. If we have 3 over 1 versus 1 over 3, this will give us a value greater than 1. The 1/3 gives us a value less than 1. So in order for this to be greater than 1, the number on the top has to be larger than the number on the bottom. And what that tells us is that we are favoring products. So if the K value is greater than 1, we say it's favoring the products. Next, we look at approximately equal to 1, and we show it here as an equal, but it's around 1. So anything really between 0 and 2 would be considered approximately 1. And what we see is that at that point, we have roughly equal values on the numerator and denominator. So we have approximately equal concentrations of our substances. This doesn't happen very often. Typically, either the products or the reactants are favored. So when we look at less than 1, what that tells us is our denominator is larger than the numerator. So back to our example with 3 over 1 versus 1 over 3. In order to get a number less than 1, the number on the bottom must be larger than the number on top. And as a result, this tells us that the substances in the reactant side, because those are in the denominator, are favored. And so we say the reactants are favored, which means the amount of reactants is greater than the amount of products.